when you're labeling the sides of a right angle triangle, you always have to pay attention to the given angle. Now, in this case, the given angle is angle X. Now, the side that's opposite angle X is this one here. We call it O. The longest side is this one here, and we call it the hypotenuse. And then the adjacent side is the side that's next to the angle, and it's this one here. And that's how you label sides of a right angle triangle. Next, you're going to discover some trigonometric ratios, and we'll consider the following similar right angle triangles. Now, similar figures are identical in shape, but not in size. So they could have different sizes, like what we have here. We have this triangle here, okay, and we have this triangle here. Now, both of these triangles are similar because they are identical in shape, but not in size. Okay, so let's write that definition down of similar figures. So I've just said that similar figures are identical in shape, but not in size. Okay, so in this case, these triangles are similar. And by the way, so what we want to do is to just discover the ratios of the sides of these similar triangles. So what I'm going to do in the next table is to write the ratios of these triangles. So the ratios of opposite over hypotenuse, adjacent over hypotenuse, and opposite over adjacent for these similar triangles. And I'm going to use this graphing package here. Okay? So this graphing package actually gives us similar triangles. As you can see, these triangles are similar. Okay? And we have the sides, and we also have an angle here. In fact, we can even change this angle. Okay? We can actually, let's keep this angle something like 45.11 degrees. Okay? So it doesn't matter, you can set it at any different angle. So what you're saying here is, in our investigation, this angle will be 45.11 degrees. And by the way, this is the opposite, this is the hypotenuse, and this is the adjacent. Now we are going to fill in this table corresponding sides of this ratios that we have here. Okay, so let's start from, we'll be getting the lengths of these ratios from this graphing package here. So on the first column, we are going to have, I'll consider the small triangle. Okay, so the small triangle first. And what I have here is 0.71. Actually, let me change it a little bit because I have 0.71 and 0. It's better if we have different lengths. So maybe let me just change this to something like 48.51 or 48.5. That's fine. Okay, so I've just changed the angle to 48.1 so that at least we have different lengths. That will be easier to work with. So 40. That's the angle again, 48.5. All right. So from the graphing package, what we have, the opposite is 0.75. So I'll just fill in here 0.75 for the small triangle. The adjacent is 0.66. Oh, sorry. Opposite of a hypotenuse. The hypotenuse is 1. So that's 1. That will just give us 0.75. All right. Next, we have adjacent of a hypotenuse, which is 0.66 over 1. So 0.66 over 1, which is just 0.66. Next, we have opposite over adjacent, which is 0.75 over 0.66. So 0.75 over 0.66. Now here we'll be forced to use our calculator to calculate that. So let's just go ahead and 0.75 divide by 0.66, and what we have is 1.13 or 1.14. So about 1.14, 1.14, rounded off to 2 decimal places. All right, let's carry on. Now next I'm going to consider the big triangle. Okay, again in the big triangle, we can see that the opposite is 1.65 and the hypotenuse is 2.2. So 1.65 over 2.2. Okay, just checking again. 1.65 and 2.2, that's correct. And we can calculate that using our calculator. So 1.65 divided by 2.2. So that gives us 0.75. So our answer here is 0.75. Okay, let's carry on. Next we have adjacent over hypotenuse, which is 1.46 divided by 2.2. So 1.46 divided by 2.2. What that will give us is, again, I have to plug this in the calculator. It's a tedious process, but it helps to understand what's happening. So 1.46 divided by 2.2, which gives me 0.66. So my answer is 0.66. Just write it properly. So 0.66. All right, let's carry on. Next, we have opposite of adjacent. So 1.65 divided by 1.65 divided by 1.46. So that will be 1.65 divided by 1.46. And that will give us, again, I have to plug it in the calculator. 1.65 divided by 1.46, which gives us 1.13. So we have 1.13. Let's carry on. So what I'm going to do in this graphing package is just to create another triangle. For example, this one here. Okay. Now, it's still a similar triangle. Remember, same shape but different size. Okay. So in this new triangle, my opposite is 1.24 and my hypotenuse is 1.65. So 1.24 divided by 1.65. Need to plug it in the calculator. 1.24 divided by 1.65, and we have 0.75 to 2 decimal places. So 0.75, the space is not enough, so I'm trying to squeeze these things. So 0.75. All right, let's carry on. Again, on the same diagram, my adjacent is 1.09 and then 1.65. So 1.09 over 1.65. Let's plug in that in the calculator and see what happens. So 1.09 divided by 1.65, and what we end up with is 0.66. So 0.66. All right, let's carry on. The next one, we have opposite over adjacent. Our opposite is 1.24. Our adjacent 1.09. So 1.24 divided by 1.09. 1.24 divided by 1.09. Let's see what happens. Okay, plug it in the calculator again. 1.24 divided by 1.09. What we end up with is 1.14, about 1.14. So the whole idea here is, if you look at these answers here, opposite over adjacent, you can see that all these answers are equal. If you look at the answers for adjacent over hypotenuse, again you can notice that all these answers are equal. So, and finally, if you look at the ratio for again opposite over this one here, if you look at this ratio, you can see that the ratio of opposite over adjacent is almost equal except the middle one, but probably this is because of the decimal places and all that, but ideally supposed to be equal. So what can we say? We can therefore conclude that the ratio of corresponding sides in a similar triangles would always be the same. Okay? The ratio of corresponding sides, so you can say that the ratio of the corresponding sides in a similar triangle will always be the same. Okay, so this idea brings us to very important concepts here. So mathematicians have labeled this ratio to be, they call it sine of this angle here. So our angle is 48.5. So this will be sine of 48.5, which is interesting. What is sine? Sine is just a name for trigonometric ratio, opposite over hypotenuse. And in fact, if you plug this in your calculator, if you plug in sine 48.5 in your calculator, so here we are, you should be able to get the same answer because it's just a trigonometric ratio. So sine of 48.5, because 48.5 is our angle here, remember? That should give us the same answer, which is almost 0.75 to 2 decimal places. Okay, so that is 0.75 to 2 decimal places, and we can see that this makes sense because that's exactly what we have. So that's exactly what we have here. Okay, and we can carry on with this investigation to give names to other trigonometric ratios. So this one here is cosine of 48.5, and this one here is tangent of 48.5. So these are names that are given to these trigonometric ratios. Okay, for example, if you plug in cosine of 48.5, cosine of 48.5, you should be able to get the same answer, which is 0.66. That's what we have here. If you plug in tan of 48.5, again, oops, sorry, 48.5, whatever answer that you get is almost what we have here. So these trigonometric ratios have special names. So the first column is sine of 48.5, second column is cosine of 48.5, and third column tangent of 48.5. And we can summarize this in the next page. So in our summary, if we have a right angle triangle, so if we have a given angle here x, and this side is opposite, let me just call it O. This one is the adjacent, and this one is the hypotenuse. We can generalize and say that the sine of x will be equal to exactly what we had in the previous page. It's opposite of a hypotenuse. Cosine of x will be adjacent of a hypotenuse, and that ratio will always be equal. And tan of x will be equal to opposite of adjacent. Now, these guys here are very, very important. Okay? These guys here are very, very important. In fact, we can come up with a way on how we can memorize these trigonometric ratios. And that is using this mnemonic. It's a helpful mnemonic for remembering these trigonometric ratios. And it's SOHCAHTOA. You can use this mnemonic to remember this trigonometric ratio. So basically, this one is for sine. So sine is equals to opposite of a hypotenuse. Actually, this is for sine, this is for cosine, and this is for tangent. Okay? So sine is opposite of a hypotenuse, cosine adjacent of a hypotenuse, and tangent is opposite over adjacent.